So today we're talking about sets, new unit completely. We are leaving algebra and factorizing behind us, although it will always be with us in our hearts. Today we're starting about with a new set, with a new unit, the unit of set. This is a completely new thing, very different, but I say it's completely new, but actually you may have seen a little bit of it in class 6. So this set notation is very modern maths. It's only been around for about a century, as opposed to algebra, which has been around for about, I don't know, maybe 18 centuries, and geometry, which has been around for 25 centuries. So basically, set notation is a relatively new thing. It starts with the notion of a set. A set is a theoretical idea, which is a collection of objects or things. So it's the notion that you can put things together and just call them a set. Now in maths, often we deal with numbers, numerical sets, but we'll see here that we don't have to have that. So usually we give the set, we give it a capital letter. So for example, you could call a set E, and this is the set of all year 11 students who study English. So you see, very creative there. We use that E to name the set for students who study English. Let's say, for example, we can have C, which is the set of all cars parked in the school's car park. We could have P as the set of all prime numbers less than 10, etc. So the way we write them down is, I'll zoom in a bit to show you more clearly. We use these strange brackets here, curly brackets for sets. So keep this in mind when you're going to write down a set. You will need to get accustomed to using this kind of notation, these curly brackets. Okay, so that's the idea with this. So if we move on to the next page, we'll see that the elements of a set, they're the objects or members of the set. So basically keep this word in mind. We'll be saying the element of. That way it sounds a bit more elegant as well. Then we use this little notation here. This looks like the Greek letter epsilon. Basically, we use this notation to mean that something is inside that set, or it's a member of that set, an element of that set, etc. Whereas if you put a line through it, it means it is not an element of that set. It doesn't belong to that set. So for example, here, if you have 2, 3, 5, and 7, 2 is a member of the set. So you would write 2, and then this symbol, and then the name of the set. So 2 belongs to this set, belongs to P. Whereas 4 doesn't belong to P because it is not inside this set. So this is the notation. This is these two notations. So belongs to and doesn't belong to. Then this n of A, n brackets of A, means how many elements I have inside the set of A. So for example, in this case, the previous one, the n of P is how many numbers we have in here, and the n of P is equal to 4. In some cases, you might look this up online. This is called the cardinality of a set. It's the number of elements in a set. And sometimes you might see it as n of A, but often in more advanced maths, you might see it as vertical brackets A. You might have this sort of thing. But anyway, let's put that on one side. And let's move on to the notion of a subset. So subsets, the element of the set S, 2, 5, 7, are also the elements of this set, which is 2, 3, 5, 7. So you see this set P is actually a larger set, which includes set S. So we say that S is a subset of P. It means that if I were to sketch it diagrammatically, basically P is this set right here. We've got 2, 3, 5, and 7 in there, but inside this set P, we've got another set S, which has 2, 5, and 7 in there. But P has 2, 5, 7, and 3 in there. So that set S is actually a subset of set P. So this is the symbol we use. It's subset. It looks a bit like less than or equal to. But what I wanted to say is that this notion here will lead us to something else as well, which is that when a set is a proper subset, so I'm skipping this in between step, I'm just going to talk about subset and set, proper subset. So subset is, the notation we use is sort of, it looks a bit like less than or equal to, really. It's like, I don't know what to call it, like a C, kind of, like a C with a little line underneath. If you remove that line underneath, you've got the so-called proper subset, which means we know for a fact this is smaller than the larger set. You might be a bit confused about this. You might think, oh, but why do we have this? What could it be exactly the same set? What do you call it, a subset? Yes, so basically, when you do not know exactly the two sets, but you know that one is definitely inside the other one, but it could actually be equal to the other one, then you use this notation, subset. But if you know for a fact that one set is like this set, 257, and the other one is 2357, you know for a fact that the other one doesn't have, it's got an extra 3. So it's got extra elements. So in this case, you would actually use S is a proper subset of P. So you would put the little c, but without the line underneath. So you would say, in this case, S is a proper subset of P.
I'm not understanding anything.
I will explain when we get to the example. I'm really sorry that this all looks a bit...
Yes, me too. It's very confusing.
Yeah, me too.
If it all looks Greek to you, it will all make sense.
So I don't know anything. Like, I'm not understanding nothing.
It will all make sense. Just bear with me. There's loads of theory. We'll get through it and then we'll get to the examples and it will make sense. Okay? Just bear with me. I know there's a lot of theory. I'm going to eventually show you an example. Now, here we say that two sets are equal if they have exactly the same elements. So for example, these two sets here, 1, 3 and 1, 2, 3. They're clearly not equal. So we can't say these are equal because they've got different elements. But these two sets, look at them, 2, 3, 5, 7 and 5, 3, 7, 2. Basically, they are exactly the same numbers, just in a different order. So these two sets are equal because they have exactly the same number of elements and the same elements as well. Okay, let's move on a bit more. I know I do appreciate that today it's going to be a little bit tricky, this notion, but it will make sense when we get to the examples, I promise. Okay, a couple more things to talk about. The universal set. Universal set is the set of everything in the question they've given you. So for example, if they give you a question where they say, we're going to take all the positive whole numbers, which are less than 20, then your universal set is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all the way up to 19. So that is your universal set. So it's all the numbers that the question is talking about. That's it, this universal set. And then finally, we've got a very modern thing, which a lot of people have a bit of an issue with, the empty set. Try to imagine this. It's a set which includes nothing inside, okay? Like an empty box or an empty drawer. It's a set which has nothing inside, okay? And we use this omicron, this O with a slash cutting through it, and basically that is the empty set, the set which contains nothing. Okay, so moving on to the final thing, promised, and then we're going to talk about examples. The complement of a set. The complement of a set is everything outside the set. So for example, in this problem, they're talking about 1, 2, 3, 4, 5, 6, 7, 8. In this problem they've given you, they say this is your universe. This is your universal set. The numbers 1, 2, 3, 4, 5, 6, 7, 8. That's it. Now we'll give you a set in here, which is the numbers 2, 4, 5, 7, 8. So if I were to show you using a Venn diagram here, we've got A, which is 2, 4, 5, 7, 8. And then outside this, we also have 1, we have 3, let's see, so 2 is here, 4 is here, 5 is here, 7 is here, and 8 is here. And then we have 1, 3, 6, and 8 outside this little circle of A. What is the complement of A? Sorry, 8 is inside A. That's wrong. Okay. What is the complement of A? Well, the complement of A is everything outside the circle of A. So what is outside the circle of A? This thing that I'm shading. Well, outside the circle of A, we've got A dash, and this is all the numbers which are not inside A. So 1, 3, and 6. So this is the complement. We call it complement because it's, in a way, it completes your set A. If you think about it, it's everything which is not in A. And that's it. We use A dash as the notation for that complement of A. And that's pretty much it with the theory. I know I've talked a lot, so I'm going to move on to an example, a hands-on example, so that people can make sense of this exercise, which I would like you to do during this session. So basically, this exercise has a few questions here. It's got 7 questions. So I'll start walking you through exercise 1 or question 1, just to give you a feel for what this is all about. Firstly, they say, this is your universal set. This is everything given in this question, the numbers between 1 and 12. So all the numbers we're going to refer to now are going to be out of this set, which are these 12 numbers. First question, what is n of u? Well, this means the number of elements inside u. So you just count these and you say, how many do we have in here? Well, we have 12. So the answer here is 12. Now, n of s means the same thing for s. You just count these numbers and write down the answer. N of t means all the numbers in t. How many do you have? Just write down the answer. Count them and write down the answers. Now, s dash. What is s dash? What is t dash? I'm going to start with just s dash as an example. So s dash is what are the elements which are not inside s, but they are inside the universal set. So let's see the number of elements, the elements which are not in s, and they're outside s. Well, we think about it this way. 2, 4, 7, 9, and 11 are in s. So what is not in s? Well, what are our numbers? They're the numbers between 1 and 12. So let's start thinking about it. This s dash means outside s. So the elements outside s. So let's draw a little picture, actually, just to help ourselves. So if we draw a little Venn diagram here, the universal set here, all of our numbers are basically the numbers 1 to 12. And they've given us a little circle in the middle, the circle of S. Inside the circle, we have 2, 4, 7, 9, and 11. Outside the circle, we have the numbers 1 to 12 because they have said in this question, this is our set U. It's all the numbers between 1 and 12. So this is the universal set. This is our universe in this question. So they've given us the numbers 1 to 12. So let's put all the numbers 1 to 12 in here. But we already know that the numbers 2, 4, 7, 9, and 11 are inside this circle of S. So what are we missing? What do we need to put outside? Well, 1, 3, 5, 6, 8, 10, and 12. So what I was looking for the missing numbers. If you imagine you've got all the numbers between 1 and 12, what was missing? Because we already had 2, 4, 7, 9, and 11. So now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we got them all. Now the question is, what is S dash? Well, S dash, which means a complement of S, it's everything outside the set of S. So everything.
That should be 1, 3, 5, 6, 8, 10, and 12.
Exactly. So S dash is 1.
I'm sorry, on the 1A, for example, on the NS there, it's 11.
Going back now to 1A, N of S means how many numbers do we have inside S? So we have 1, 2, 3, 4, 5. N of S would be 5 here. And then you do the same thing for T. Here we've got some questions which are true or false. This would mean S is a subset of U. So the question is, are these numbers here, 2, 4, 7, 9, and 11, inside this set here, the numbers between 1 and 12? The answer is yes, they are. Because, well, it's true because that's how the question was given. They gave us the numbers between 1 and 12, and then they gave you the set S, so that these are numbers out of this set. It's been designed to be this way. But then the next question, look at this. Is S, this set here, 2, 4, 7, 9, 11, a subset of T? So is this set inside the set T, which is 4, 11? Well, clearly, no, because this set has 1, 2, 3, 4, 5 numbers. This one has 2. How could this fit into that? It's impossible. So here we say this is false, because one set is not actually inside the other one. This set is not inside that. And then we have a similar question coming up. Is T a proper subset of S? So what they're saying is, are these two numbers, 4 and 11, entirely included inside S? Well, the 4 is, the 11 is there. So yes, indeed, yes, this is true. And then basically we've got plenty of questions here. I think what I'll do, guys, is I'll stop recording here because I don't want it to drag too much. And I'm going to be guiding you as you work through this exercise. Just give me a second to stop recording here, and then I'll give you some time to ask questions.